Okay, so here we discuss the cross view. Cross view in Chinese is 正交场. Okay, so here is a plural. Okay, so which means we have two views here. Okay, so one of them is E view and the other one is B view. Okay, and these two views are both of them are uniform and they are perpendicular to each other. Okay, so 它们就是均匀，而且它们互相垂直的方向，所以我们把它叫做 cross view. Okay, so yeah, so here the subtitle, actually the title is the discovery of the electrons. Okay, so 是电子的发现啊，电子的发现。Okay, so there are quite a lot of text, but simply speaking, it tried to use a apparatus, 用一个仪器 to measure the ratio of mass, to charge, 就是算一下这个电子的质量跟它的电荷的比例啊，跟它的电荷的比例。OK， 简单来说，我就不看，我直接看图。OK, so let's directly take a look at this figure. Okay, so starting from the left hand side, okay, we have a battery here. Okay, we have a battery here. So for this loop, okay, it will try to make some electron. Okay, make some electron that can go starting from here to go to the right side. Okay, follow the orange direction. Okay, if it's not going to the orange direction, maybe it go to here, it will be absorbed. Okay, so the only direction it can go through. Okay, here we have a small slit. Okay, 就是有一个很窄的有一个狭缝。Okay, so if the electron is going through this slit, okay, it can go through. Okay, it can go outside. Otherwise, it will be absorbed here. And starting from here and then up to here, we have another battery. Okay, which means inside this region, we have a E field. We have an E field actually pointing to the left side inside this region. Inside this region. Okay, so in that way there will be a force acting on this E electron. Okay, so it will accelerate pointing to the right side. Okay, accelerate 就是往右面加速，就是通过这个狭缝出去。OK， 所以这边开始静止一路加速到这里，那就是有这个 QV 或者是 EV， 就是提供它的能量给它就是这里会有一个终端的速度射出去，那外面的话就没有这个电场了这个 for this battery it only generate E field within this region. Okay, so outside we have another structure. So here we also try to make the right hand side to be vacuum. Okay, so 让右手边真空用右手边真空。如果有空气的话，电子有可能会碰到那些空气的粒子就会影响到这个实验，所以它让右手边是真空的。Okay, so here we have the cross view. Okay, so for the E field, it used the green arrow to identify there is an E field pointing downward. Okay, so we use parallel plates. To generate this uniform E field pointing downward. Okay, so this is positive side, this is negative side. So the E field pointing downward, and then also we have the B field pointing into the page. Okay, so these two B field. Okay, so for this B field, we just forget. Okay, how we can generate this B field. Actually, we can also use a big magnet. Two magnet pair to generate this B field. But the most important point here is B field and E field are perpendicular to each other. Okay, so there should be some force acting on this electron. There should be some force. Yeah, because individually For E field, it will generate, I should say there should be a Coulomb's force acting on the charge. And for the B field, there should be a Lorentz force, okay? So there is a Coulomb force, Coulomb force, Coulomb's force, and also the Lorentz force, Lorentz force, okay? So, but here, this part is very strange, So here we also assume that the net force acting on this electron is perfectly zero. So that the net force acting on the electron is zero. So there won't be any other acceleration here. Okay. So starting from this point all the way to there, there should be only the all the way it should be a uniform velocity movement. OK， 就是一个匀速的运动，从这个缝隙开始，外面的话，它没有任何力作用在身上包括我们忽略那个 gravitational force 把重力忽略掉Okay, so here there should be two forces. Okay, so here we try to assume they perfectly cancel. So at least inside this region. Okay, so we assume that this B field, E field are only present inside this region. Or outside there won't be any B field and E field. Okay, so here, as much as the charge is negative charge, okay, so which means the Coulomb's force is actually pointing upward. Okay, the E field pointing downward, it is a negative charge, so the Coulomb's force is pointing upward. Okay, Coulomb's force is Fe, and for the Lorentz force we denote it as Fb. Okay, for the Fb we need to use the right hand rule. Okay, so first of all, Q is pointing to V is pointing to the right side. Okay, Q is negative, and then B is pointing into the page, shown in the green cross. Okay, there. So V is pointing to the right side, and then B is pointing into the page. Okay, so cross it like this. The thumb is pointing upward, so this is the direction of V cross B, but this is an electron is a negative charge. So our thumb is pointing downward. Okay, so like this. Okay, so this is Fb. This is Fb. Okay, so using this structure, we can verify that the charge, or at least the electron, is a negative charge. If it's a positive charge, we should swap the polarity of the capacitor so that it will reverse the direction of E field. Okay, but that's not the case. So with these settings, okay, we can have some tuning so that we can equalize Fe and Fb, so that the electron can go straight to shoot on the middle part of the screen. Okay, so what does we tune? Okay, we need to make sure that Fe is equal to Fb. Okay, so here Fe is E. Okay, we just ignore the positive or negative sign. Okay, we just care about the magnitude because we have already discussed the direction here. Okay, so here we just assume that Fe is E times the E field. Okay, the E field magnitude equals Fb. Fb is QVB. Q is also E, and then V, and then B. Okay, here we also assume that V and B are perpendicular to each other, so sine of 90 degrees is 1. Okay, so here we can just cancel this E and E. Okay, so it turns out to be V equals E over B. Okay, so what we need to do is we need to make sure that the magnitude of the E field and B field to be the velocity. So, but the velocity here is related to this battery. Is related to this battery. So yeah, so this is somehow like this. So this velocity will be, so you can also use some conservation of energy. So this energy will be E times V, and E times V will be 1/2 mv square like this. So we can get the value of V here, okay? And then we try to plug in V equals E over B here so that we can know the relationships. So how do we adjust all these parameters so that it can make the electron going in a straight line, Okay, so here we have other topic called the Hall effect. Hall effect is very important. So here it says, as we just discussed, a beam of electrons in a vacuum can be diffracted by a B field. Okay, can the drifting conduction electron in a copper wire also be diffracted by a magnetic by a B field? OK， 所以这个 Hall effect 很重要的意义是在于，它也论证了这个导体里面的电流，它流动的粒子或者是流动的电荷一定是负电荷，它是一个负电荷，朝着这个电流的反方向移动，而不是说正电荷朝着电流的方向移动，所以它论证了这一点。我后面的话就会说明一下为什么它有能力这么做其他很多的实验，其实你假设说正电荷往正方向动，或者是负电荷往负方向动，其实它们都没有冲突。但是对于这个 Hall effect 来说的话，它就告诉你说，它一定是负电荷在动。Okay, so in 1879, a 24-year-old graduate student, 这是 at the Johns Hopkins University, okay, 一个24岁的研究生And then, so the Hall effect allows us to find out where the charge carrier in the conductor are positively or negatively charged. Beyond that, we can measure the number of such carrier per unit volume of the conductor. Okay, so here we try to make quite a lot of assumption. Okay, so starting from this figure A. Okay, so here we have a wire， 就是我们有一根导线，and then the width of it is d， 就是这个宽度是 d，and then we assume there is a current going from top to bottom， going from top to bottom。Okay, so here we already assume that the charge is negative. Okay, so after finishing all this argument, I try to repeat. If this charge is positive, then we will find some conflict. Okay, 就是我们后面如果假设这个是正电荷的话，就会出现一些实验会矛盾的结果了。所以论证出这个移动的电荷一定是负电荷。Okay, so here we just assume that this is a negative charge, so the Vd of this negative charge is moving upward. Okay, and we also generate an external B field pointing into the page. This is pretty much all of the setup of this experiment. Okay, so in this case. Okay, so as much as we have a moving charge in the B field, so there will be Lorentz force. So V cross B, V is pointing upwards, B is pointing into the page, so V cross B is pointing to the left side. Okay, so V cross B is pointing to the left side, and this is a negative charge, so FB point to the right side. Okay, so we just keep in mind that there will be FB pointing to the right side, so which means the Lorentz force will try to push the electron to the right side. So in such a way, the negative charge will accumulate on the right side. And there shouldn't be any excess charge for the wire. So which means there should be something like an induced charge on the right side. Okay, induced negative on the right side. And so as much as some of the electrons are going to the right side, there should be positive on the left side. So which means in such a way we have some positive charge on the left side and then negative charge on the right side. Okay, so in such a way, as much as we have these two charge distribution, it will generate E field inside the wire. Okay, so in this case we have some E field inside the conductor because there are some B field. So in such a way, this E field pointing to the right side, and this is a negative charge. So due to this E field generated by this charge distribution, there will be Coulomb force also acting on the charge. Okay, so Fe point to the right side, point to the left side. Okay, as much as E field point to the right side, and then it is a negative charge. Fe point to the left side. Okay, so in such a way, as much as there will be more and more charge, more and more negative charge accumulate on the left side, the E field becomes stronger and stronger. At the beginning, there is no E field, E is 0, and then the negative charge start to accumulate, becomes larger and larger on the right side. So the E field becomes stronger and stronger, and so the Fe is also stronger and stronger. Fb is actually a constant. It doesn't change at all. As much as if we don't change the current. If you still remember, J equals NEVD. Okay. So and J is proportional to I. Okay, if we don't change the I, the J doesn't change, and then this is a constant, so VD will be a constant. So if VD is a constant and then B field doesn't change, FB should be a constant over the whole experiment. Okay, so FB doesn't change. FV starting from 0 becomes stronger and stronger. So when this negative charge is large enough, Fe will become large enough to be equal to FB. OK， 所以这个 Fe 越来越大，大到某个程度的话，就 Fe 跟 FB 越来越大，那就不会再有更多的电荷累积在右手边。OK， so in such a way there won't be any. OK, as much as Fe is equal to FB, then there won't be any additional charge accumulated on the right side, and it will become an equilibrium condition. OK， 就进入一个平衡的状态就会像这样。OK, so in the experiment, actually we can really measure this. OK, we can really measure the potential difference from the left side to the right side, because this is positive charge, this is negative charge. So if we use a voltmeter, to measure this point and this point, okay, we will be able to measure the potential difference. And actually, we can measure the potential is higher on the left side and lower on the right side. So this V equals E times D is what we can measure. And also, at the equilibrium state, we should have Fe equals Fb. Okay, for the Fe it is Q times E. For the Fb it is Q times Vd times B. Okay, so similar to what I write previously. So this is nothing but the Coulomb's force. This is nothing but the Lorentz force. Okay, so they are equal to each other, And also we have J equals NE times VD, so VD equals J over NE. And J, okay, we also assume that the current density is uniform, so J is I over A, so VD becomes I over NEA. Okay, so we altogether have these three equations, and finally we can get N equals this expression. So what we have eliminate, actually we have eliminate E. Okay, so we can just multiply these three equations together. So on the left side we have capital V, we have Q, we have E, we have VD equals ED times Q VD B times I over NEA. Okay, so quite a lot of stuff. We can do many cancellation. So this Q and this Q can be cancelled. This VD and this VD can be cancelled. This E and this E can be cancelled. Okay, so on the left side, we only have this V remains. And then on the right side, we still have this D, this B, and then this big thing, okay? Okay, so finally, we try to put N to the left side, and then put V on the right side. So N on the left side, okay, this one, and then we have B times I on the top, and then this V will go to the bottom, and then also we have EA, and then also D, EAD, D on the, maybe I can write it as D over EA, something like this. Okay, or maybe I can just put E here, E here. Okay, so the remaining stuff is this L, okay, this L should be A over D. What is A? A is the current density, which will be the cross-section area. Okay, the cross-section, we suppose this is a circular. Okay, this is a cylindrical wire. So this is the cross-section area, or maybe this is a rectangular one. This is a rectangular one. Okay, so the width is D, and then this is L. This is L. Yeah, so actually the L here, is A over D, which is the thickness of the strip. So with this equation, we can find N from measurable quantities. Okay, so finally this one becomes 1 over L. Okay, so which is the here. Okay, so actually it says if we use this formula, we have N to be B. B is what we know, okay, because we generate the external B field, so we know this value. The I we also know, okay, it is easy to measure. For this V, it is the Hall effect potential, okay. This is actually can be measurable using a voltmeter from the left side to the right side. And then this L is the dimension of, this is the thickness, of course we also know. And then finally the E, okay, the E is elementary charge. So all these 5 values we can get the values, so that based on this equation we can find the carrier density or the charge, not necessarily the charge, okay, the charge, this equation we can find N for measurable quantities, which is the carrier density. The carrier density 就是 这些电荷的数目单位体积的电荷数目。Okay, when a conductor moves through a uniform B field at speed v, the Hall effect potential difference V across it is V equals VBD. Okay, so this is a very important very important formula we can easily use. Yeah, how we can get that? We just make use of the first two equations. Okay, so we multiply these two together, so we get V times QE, okay, equals ED times QV. Okay, VD I just write it as V, and then capital B. And then we can do some cancellation. Here we cancel Q and Q, cancel E and E. So finally we get V equals VBD, okay, VBD like this. Okay, so this will be the Hall effect potential difference, will be the velocity of the carrier multiplied by the B field multiplied by the width, multiplied by the width of the strip. Yeah. Okay, so just now I mentioned that if we assume the charge to be positive, there will be some conflict. Okay, so let's consider if here we have a positive charge, and then the B field is pointing into the page, and then also the current is pointing downward. Okay, all this stuff do not change at all. So in that case, VD is pointing downward, okay? Because if it is a positive charge, it should have the same direction as the current. Okay, so VD pointing downward, B is pointing into the page. So in that case, V cross B, V is pointing downward, and then B is into the page. So V cross B, okay, V cross B is pointing to the right side. V cross B. And also FB is pointing to the right side. FB is pointing to the right side. So or Q or V cross B, okay? Because Q is positive. So we have a FB or V cross B pointing to the right side. So in such a way, this FB will push all this positive charge to the right side. It becomes something like this: positive, 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 and then negative on the right side. Should be something like that. But this will be conflict with the measurement. Yeah, because actually with this setup, we actually can measure that there will be a higher potential on the left side and then lower potential on the right side. But if it is a positive charge, and all the other settings are actually the same. We just assume, if we assume the moving carrier is a positive charge, then this positive charge will accumulate on the right side. So in such a way, there will be a high potential on the right side, which is conflict with the measurement result. So this means this Hall effect experiment verify that the moving carrier in the conductor wire should be a negative charge. Okay, so far any questions? 有没有问题？ Okay. So here we have a sample problem. So it says a solid metal cube of edge length d moving in the positive y direction at a constant velocity of magnitude. Okay, 4 meters per second. The cube moves through a uniform B field of magnitude 0.05 Tesla in the positive z direction. Which cube phase is at lower electric potential, and which is a higher electric potential because of the motion through the field? Okay, so here we don't try to provide a current, but if we try to move this cube inside a B field. Okay, if the moving direction of this cube is perpendicular to the B field, then there will also be Hall effect. There will also be Hall effect because there will be free electron inside the this is a metal, right? Yeah, a metal cube. Okay, there will be free electron. So if we only move this cube, then it is equivalent to there is a moving charge. Okay, so there will be Lorentz force. There will be Lorentz force, and if it is Lorentz force, then there will be Hall effects. So in that case, we can just use the right-hand rule, okay, to determine the direction of the Lorentz force. So V is pointing upward, B is pointing out of the page. So V cross B is pointing to the right side. So FB is pointing to the left side. FB is pointing to the left side. FB is pointing to the left side, which means for this side is negative, okay, because the negative charge, okay, there will be Lorentz force acting on the negative charge pointing to the left side, so there will be negative charge accumulating on the left surface, and in such a way there will be okay, let's see, there will be positive charge accumulating on the right side, So this is really simple. Okay, so this already answered the first question. Okay, so which cube phase is at lower electric potential? So the left phase with at lower potential. Okay, and then the right phase at higher potential. Okay, so this is easy to determine. Okay, so for question B, what is the potential difference between the phases of high and lower electric potential? So we just make use of V equals small v times B times D. Okay, so here we already know V is 4, and then B is 0.05 Tesla, and then D is 1.5 centimeter, so which is a 0.015. So this is nothing but 3 millivolt. Although this is not large, but this potential difference of this voltage is still measurable. With a normal lamp device. 就是普通的电表是可以测到这个 millivolt 的，很普通的那个电表就可以测到这个3毫伏这个电压。Okay, so this is easy. So next, we also talk about the circulating charge particle. So here we assume there is a B field. Okay, there is a uniform B field. Uniform B field is direct out of the plane. Okay, direct out of the plane. Let me use this color. The B field, okay, the B field is pointing out of the plane. Okay, so if so here there is not a cross field anymore. We only have the B field, uniform B field pointing out of the page. Okay, so here if electron, okay, here we have an electron entering this B field. Okay, so here at the bottom we have a generator. It tries to shoot it try to shoot. Okay, so this G is a generator. It try to shoot an electron. Okay, like this direction. Okay, so at the very beginning, okay, this electron is moving to the right side. Okay, so at that moment, there is already a Lorentz force acting on it. Okay, so for the Lorentz force, we're acting on it to make it like turning to the left side. Okay, so or maybe on this point. Okay, so the velocity is pointing roughly pointing upwards. Okay, upwards, and then the B field is pointing out of the page. So V cross B is pointing to the right side. This is V cross B, and this is an electron. Yeah, electron is a negative charge, so FB pointing to the left side. Okay, so this is a circular motion. Okay, so it turns out to be a circular motion. Actually, you can use some math to prove it rigorously, but I don't try to do that. Actually, you are familiar with mechanics 就是力学很熟悉了，所以的话就是说，这个 FB 就会变成一个 circular motion 的向心力嘛，就是那所以的话就是这个 F， 这个是 F 等于 mv 平方除以 r， 就是 F 等于mv 平方除以 r， 就是这个。那这个 F 的话就是这个 FB。So FB is actually QVB. Okay, so these two are perpendicular to each other, so we don't have this sign of 90 degrees. And then LV is square over R. So we can slightly rearrange the term, so moving R to the left side and then move this stuff to the right side. And then actually we can also cancel this V with this V. So we can get R equals mv over qb. So in such a way, the radius of this circular motion is tunable. For the mass of an electron is fixed. Okay, this is 9.1 times 10 to negative 31 kilogram. Okay, so this is a constant. The velocity is a variable. Okay, so this v is proportional to r, and then this q is actually e, 1.6 times 10 to minus 19. This is also a constant. So the final thing is the B field. Okay, we can actually change the magnitude of the B field. So more or less the only controllable variable is this B. Okay, we can adjust the B field to be stronger or weaker so that we can following this equation, we can have different R and B pairs, something like that. Yeah, so this is the circular motion. Okay, so here we have a sample problem. Okay, so this is an electron with a kinetic energy of 22.5 eV move into a region of uniform magnitude, uniform B field of magnitude. This one, and then the angle between the directions of B and electron's velocity is 65.5 degree. What is the pitch of the helix path taken by the electrons? Okay. 所以的话，如果 V 跟 B 是完全垂直的话，它就是圆周运动。那现在的话 ，V 跟 B 不是完全垂直，所以的话，它可以分两个分量。那这个 V 就会变成一个 V 的垂直，一个 V 的平衡啊。那所以 V 垂直跟 B 它们之间是垂直，所以这两个就会产生一个在这个平面上的圆周运动。那这个 V 平衡的话，跟这个 B 就没有作用，所以的话，这个电 这个电子啦，这个电子就会这个应该是负电荷吧 ，electron 应该是负电荷。那这个电子的话，就会在这个方向，这个 z 轴的方向做一个匀速运动。那这个匀速运动跟这个圆周运动加起来的话，它就会变成一个螺旋线就会变成一个螺旋线，就是这样。Okay, so actually it asks you the pitch of the helix path. The pitch means for a circular motion, okay? So let's say if you project this helix to a plane, okay? So for this cycle, and the next cycle, okay, it corresponds to the same point for the circular motion. And actually, this pitch is the distance between adjacent point of these two helix path, okay? 所以这个叫做 pitch。就是在同一个圆周运动的这个点上面这相邻的螺旋线，它们相隔多远，就是这个 pitch 这个我印象中之前 quiz 好像或者是考试常常考这个 helix 然后通常考试的时候都很多人问这个 pitch 是什么啊？很多人问的，这种立体都有然后后面好像selectable 也有的但是通常都是很多人会问的Okay, so here what we need to find is the velocity first, because at the beginning we only know the kinetic energy. So V equals square root of 2k over 2m. Okay, sorry, it's 2k over m. 2k over m. Okay, so this is square root of 2 times 22.5 eV times 1.6 times 10 to minus 19. Okay, so this is in joule. Okay, over electron is 9.11 times 9.11 times 10 to minus 31. So this is 2.81 times 10 to the 6 meter per second. Okay, so this is the velocity for this one. Okay, so there's an angle of 65.5 degree. So we have P should be equal to V parallel T, which is V cosine of phi. Okay, so here this is the phi. Phi is the angle between V and the B, So this is V parallel. Okay, V parallel. Okay, so this is V parallel multiplied by the period of the circular motion. Okay, so how do we find the period? Okay, so actually the period should be like we have 2 pi r will be the circumference of the circle. So it will be this V times the period. Okay, V times T will be the distance. Okay, so actually T will be 2 pi r over V, and then we plug in r here, so we will get T equals 2 pi over V and then times mv over qb. Okay, so V and V cancel. We have 2 pi m over qb. 2 pi m over qb. This is the period. This is the period of the circular motion. So this is 2 pi m over qb. Okay, so now we just need to plug in all the numbers. 2.81 times 10 to the 6th power, and then cosine 65.5 degree, and then times 2 pi times 9.11 times 10 to negative 31 over 1.6 times 10 to minus 19 times B is here, 4.55 times 10 to negative 4. Okay, so use a calculator, you can find this is actually 9.16 centimeter. 9.16 centimeter。OK， 所以这个就是 pitch 啊，这个就是 pitch。OK， Oops, that's not that anymore. This is much.